So moving on to molecular compounds now. So molecular compound is made up of two non-metals. All right. So they work considerably differently than ionic compounds. In ionic compounds, it's all about balance. Somebody's got to give up electrons. Somebody's got to want to take them away. Charges have to work out to zero, all of that kind of stuff. That is so not the case with molecular compounds. Okay. Because if we look at the things they're made up of, non-metals, all non-metals have what kind of charges? They're all negative. Okay. Well, I can't put two negatives together, okay, and suddenly have positive charges coming out of that. Okay, it's like saying two wrongs don't make a right, but three do. No, they doesn't. Okay, but yeah, if we put all these non-metals together, we're not going to get positive charges out. We're not going to get the charges to balance, and we're not going to try because there isn't an exchange of electrons going on in a molecular compound. There's a sharing, okay, which makes molecular compounds way more stable than their ionic counterparts. Okay, ionic compounds, like we said, you throw them in water, they dissociate right away. Okay, it's really hard to separate molecular compounds because they're so dependent on each other for those electrons. They're sharing them, and if they get separated, they won't be happy anymore. Okay, molecular compounds are like true love. Okay? I know I said don't put a sociological thing on it, but you can't separate these two things. Okay, they are so dependent on one another. They have what the other needs, and they're sharing it as opposed to just giving it away. Okay. All right. So what we have here in, let's say, an example is water. Okay. So in a water molecule, so that's what we see here on the left. Okay. We've got two hydrogens, so that's the green nuclei. So here and here. Okay. And then we have our oxygen atom over here. So in our oxygen atom, okay, the first shell, like a Bohr diagram, has the two atoms in, or sorry, the two electrons in it. Okay. And then the next shell has, it can hold 8. But when oxygen's by itself, it only has 6 in it. Okay, so when it's got the 6 in there, it still has space for 2 more, which is why it works out really well to find 2 hydrogen atoms. They need another electron to fill their outer shell. Okay, they only have 1. But when they bond together, okay, we get this sharing. Okay, now hydrogen is kind of happy because it's got 2 electrons in its outer shell. Oxygen gains another one. Same with this one down here. They're sharing them. Okay, so what we call a covalent bond because they're sharing their outer shell. Covalent. The outer shell is always called the valent shell. Well, again, that's the problem with the Bohr diagram is it looks like they're very close. It doesn't really end up being this way. It's just easier to visualize it this way. Okay, you're right. If I put 2 electrons that close together, they would repel. Okay. Now, what ends up happening with water, because water's weird. I mean, we all know that, right? If there's any rule in nature, water's the exception to it, right? Right? Like when you freeze water, water gets bigger, right? Everything else gets smaller. Okay, stuff like that. So, it's weird things, but that all has to do with kind of how these electrons are shared, and we're going to get into that later in the unit. But for now, okay, we're just going to look at with all molecular compounds, they have a covalent bond where they're sharing the electrons, and as a result, they hold on very, very tightly to each other. Right? That does, however, mean that molecular compounds are generally less like their ionic compound counterparts, okay, in terms of their behaviors, right? Which is something we're going to need for the first lab that we do. We're going to be identifying unknown compounds based on their physical properties. Okay? And molecular compounds and ionic compounds behave very differently. Okay? So that'll be one of the ways we can separate them. All right, so big thing with molecular compounds, nonmetals usually have negative charges. No one element gets to keep the electrons, so the electrons are shared. Okay? That's the big thing. Since electrons are shared, is there more than one way that 2 elements could go together? Yes. Okay. Hence the reason why we use prefixes when we're doing the naming for molecular compounds. Okay. We said in an ionic compound, when calcium goes with bromine, there's only one way those 2 things go together, with 2 bromines and 1 calcium. Okay. The charges have to balance. In a molecular compound, that's not the case. That's why we need the prefixes, because there's a number of ways that any 2 elements could go together. Okay, so when we're naming molecular compounds, like we said, they arise when two or more nonmetals react to form a substance. The electrons get shared. Okay, the difference between naming the ionic compounds and the molecular compounds is that molecular compounds will use prefixes to denote the number. Okay, so. All right, so if we're looking at this one here, CS2, this would be carbon disulfide. All right. If this, with this stuff here, N2O, this would be dinitrogen oxide. Actually, that's not right. That's a typo. Monoxide. Okay, the "ide" suffix, again, only goes on the second material. Okay, I don't go like carbide disulfide. I don't put "ide" on both of them. Okay, I only put "ide" on the second one. Mono only goes on the second one. You'll see here that, I mean, there's only one carbon here, but I didn't put monocarbon disulfide. Okay, mono, for whatever reason, it's just chemists being difficult. Okay, they got to have funny rules so people can forget stuff. All right, so mono never goes on the first one, but every other prefix does. It does. Whatever order the formula is written in is the order you write the name in. Right? So if we wrote it as CS2, then we write carbon first and sulfur second. Okay, now that means we need to know our numeric prefixes up to at least 10. Okay, so if we don't remember those, okay, let's quickly write those down. So 1 is mono, okay, 2 is di, 3 is tri, 4 is tetra, 5 is penta, 6 is hexa, 7 is hepta. If you took Science 9 in French, you may have been taught that it's septa. Don't use that. Mr. Real hates it. Okay, he will. That's one of his triggers. Okay, you got to watch out for that one. Okay, it's one of his triggers. 7 is hepta. Okay, 8 is octa, 9 is nona, and 10 is deca. Okay, shouldn't need anything beyond that. Not in chemistry. Yeah. It is in other like linguistic uses, but in terms of like in a numerical designation on a technical term, then it should be di. Right? We don't say a dicycle. Right? It doesn't make sense in that sort of language, but yeah. Okay. These molecules up top here, okay, are they compounds where I have 2 hydrogen atoms bonded together, 2 oxygen atoms bonded together? Are those compounds or are they just molecules? They are, right? Okay, they're diatomic elements. Okay, they're what we call our molecular elements, is what we sometimes call them. Okay, this is not a compound because it's still the same element. Okay, some elements bond to themselves. Okay, that doesn't make them a compound. A compound has to contain different elements, like these ones here at the bottom. Right, so we want to make sure that we understand that there's a difference between a molecular element, that's the top row, okay, and a molecular compound, that's the bottom row. A compound has to have 2 different elements in it. All right. Now, on that note, on your periodic table, you may want to highlight or somehow color in, okay, or indicate which are the molecular elements. Okay, so we're going to do that here in just a sec. Okay, so on your periodic table, you need to come up with some kind of color code, but you don't necessarily have to do the coloring right now, but you at least need to identify the elements that are what we call molecular elements. That is, they will bond to themselves. Okay, now I have them in different colors because there's different ways in which they do this. Okay, anything that's colored as yellow, so that would be nitrogen, oxygen, fluorine, chlorine, bromine, iodine, and astatine. Are what we call the diatomic ones. They come in pairs. Okay, so we would have N2, O2, F2, Cl2. They come as twos, as sets of 2. Okay, hydrogen also needs to be colored in or indicated as a diatomic or yellow element. Okay, because hydrogen also does that. Okay, phosphorus and sulfur are also molecular elements, but their molecules are bigger. Okay, phosphorus comes as a quadruplet. Okay, that is, when phosphorus bonds to itself, it does so 4 times and comes in a group of 4 phosphorus atoms, or P4. Okay, and sulfur is even bigger. The sulfur comes as an octuplet. Okay, so when sulfur is by itself as an element, it's S8. It bonds to itself 8 times. Okay, and so we get this group of 8 sulfur atoms together. Okay? That's not going to be super important for us to know until we get to reactions, but it's just, we're just talking about the difference between a molecule, a molecular element, and a molecular compound, so it's a good time to just indicate them on our periodic table. So what I would like you guys to do right now is try the first 4 of these. Okay, they're all molecular, so just give them a try and see if you can get the proper molecular names for the first 4. Okay, and then we'll go over them together and see how we're doing and try the others. So our first one here, we've got 1 nitrogen, 3 iodine, so this is going to be nitrogen triiodide. Okay. And typically we hyphenate that, but I wouldn't mark it wrong. I know English teach, so I don't know if that's right or wrong to hyphenate it or not. Okay. All right, number 2. Okay, we've got carbon, 1 carbon with 4 iodines, so this is going to be carbon tetraiodide, right? I'm not sure if that's why or not. Aren't you guys too young to know what Tetris was? Tetris was huge when I was in like junior high school. That's how old Tetris is. Okay, for number 3, okay, we've got 2 nitrogens now. So do I need a prefix on the nitrogen? Okay, and I've got 3 oxygens. So this is going to be dinitrogen trioxide. Okay, and for number 4, we've got 1 tellurium and 2 acetatides. So this is going to be tellurium diacetatide, right? Okay. Seeming familiar? Okay, question. They behave mostly as what the side of the staircase they're on, but metalloids are not something involved in a lot of compounds. They're quite rare, so it's not something you're going to encounter very often, right? But for now, just name them with the usual naming rules. Okay, David, try up to number 10 there. See how we do on those. Okay, so let's look at number 5 here. So I've got 2 phosphorus and 3 sulfur. So this is going to be diphosphorus trisulfide. Okay, and number 6, we've got 1 oxygen and 1 sulfur, excuse me. So this is going to be oxygen monosulfide. Okay, 7, we've got 3 silicone and 4 phosphorus. So this is going to be trisilicone tetraphosphide. What are you noticing none of my names have? Right. Okay, remember that's something we need to be working on here. Okay, is getting out of the habit of using capital letters on those. Okay, for number 8, I've got 1 sulfur, 2 chlorines. So this is just going to be sulfur dichloride. Okay, and for number 9 here, 1 silicone, 4 hydrogens. What's hydrogen acting as in this case? Non-metal, right? It's listed second. Okay, so this is just going to be silicone tetrahydride. Okay, and this stuff here is going to be tetraboron tricarbide. Not that all of those actually exist as real compounds, but it's just a naming exercise. So, okay. All right, questions on any of those? Making some sense? Seeming familiar, hopefully? Okay, now we will, I don't know what happened to those. That's weird. Okay, anyway. Now, here's something that is new for you, okay? Well, it's not. There's a couple that are new in here because there's a couple that have the polyatomic ions we talked about a little bit earlier, okay? But this is a mix now. Some of these are molecular. Some of them are ionic. Some of them need Roman numerals, maybe. Yes, some of them need Roman numerals, okay? Some of them have polyatomic ions. Now you got to be able to identify on the fly which one's which, okay? Apply the right naming rules, get them right. This is a more realistic kind of, let's say, almost like what a quiz next week might look like. Okay, it wouldn't have 15 of them, but okay, it would have just fewer than that. Okay, so for number one, is this an ionic compound or a molecular compound? It's ionic. Lithium is a metal. Okay, so this stuff is simply lithium chloride. Okay, second one. It's ionic and it requires Roman numerals. Chromium has more than one possible charge. Okay, so we are going to have chromium something fluoride. Okay, fluoride is always a -1 charge, and there are 3 fluorides. So that means there's a total of 3 negative charges. Okay, that means I need to get 3 positives out of the 1 chromium, so that chromium is +3. So this is chromium 3 fluoride. Okay, lots of little things we always have to be checking for, and that was the idea behind this exercise. Okay, how aware do I have to be when I'm looking at these things? Okay. All right, so for number 3, we've got phosphorus and bromine, ionic or molecular? That's molecular, so we were going to have phosphorus tribromide. Whoop. Okay, number 4, ionic or molecular? Ionic, zinc is a metal. Yeah, so this is zinc iodide. That's not a capital. It looked like a capital. Okay, and for number 5, I've got silicone and oxygen together, molecular, ionic, molecular, silicone dioxide. Okay, give you a few more minutes here and I'll do another 5. Okay, so for number 6, I've got carbon and sulfur together, molecular or ionic? Molecular, okay, carbon is a non-metal, so we've got carbon, Tetra, sulfide. Okay, for number 7, we've got technetium and iodine, ionic or molecular? Ionic. Okay, so this is no prefixes, technetium iodide. All right, number 8, first one that has a polyatomic ion in it. All right, and we said we don't change what we do. We name the metal first, and then this is acting basically as a non-metal because it's second, okay? And we don't change the ending of a polyatomic ion. So this stuff is going to be sodium hydroxide. Okay, this stuff is incredibly basic. It's the stuff that's in oven cleaner. So it's very, very corrosive if it can dissolve the baked on crud from the inside of your oven, right? That's what it's basically used for, right? You don't want to get this stuff on your hands or inhale it or anything. It'll give you very severe chemical burns. Okay. All right, number 9, we've got calcium with sulfate, and there's a mistake with the way I've written this formula. What is it? Yeah, I shouldn't actually have those brackets there at all. I didn't put a number outside of them, so they really shouldn't be there. It's kind of nitpicky, but those brackets really shouldn't be there because I didn't need to put any other number outside of them, right? So we typically don't write them if we don't have to. So this stuff here will be calcium what? Sulfate, right? Again, we don't change the ending of a polyatomic ion. We leave it as it is. Because if I change this to ide, suddenly this stuff and CAS have the same name and they're not the same thing. All right, and then for number 10, okay, K is potassium, and what's MnO4? Permanganate. Yeah, this stuff is potassium permanganate. used to do a lab with this stuff when I taught in Lloydminster, and I had a kid who never listened to me. And I told them, when you're handling the potassium permanganate, use the scoop or tweezers. It's little purple crystals. They're quite pretty, actually. Okay, and this kid never, ever, ever listened to me. This issue with potassium permanganate is that it looks pretty, but as soon as it comes into contact with your hands, it reacts with the oils and moisture on your skin. And it goes from being a very pretty purple to a kind of disgusting looking brown color. And I knew this ahead of time, which is why I told them repeatedly, don't touch it with your hands. Okay? Because if you have like very light colored skin, it's going to turn the tips of your fingers brown in such a way that it will make people question what you've been doing. He didn't listen to me. And as a result, he had these brown tipped fingers for like 2 weeks. It was like the most poetic justice ever. Okay. How do I get this off? Well, I don't know. You go home and use sandpaper and bleach. I don't know. You're pretty screwed. You probably should have listened. So, hey, by the way, you should really listen if I tell you something like that, because I'm that guy that'll let you find out the hard way as long as it won't hurt you. This didn't end up hurting him in any way, but it was really funny. Okay. All right. How many people have done the last 5? All right, let's go through those 2 then. Okay. So for number 11 here, we've got molecular or ionic? Molecular. So this is nitrogen. What prefix do I need on the oxygen? Mon, yeah. We typically don't write monooxide, we just write monoxide, but yeah, I wouldn't mark it wrong if you wrote mono. Okay, 12, we got beryllium and cyanide, ionic or molecular? Molecular, so this is just beryllium cyanide. All right, number 13, we have barium with cyanide, ionic or molecular? Ionic. So barium, cyanide. Well, no, one's beryllium and one's barium. Yeah. Oh. I'm not going to say I would never try and trick you. I will sometimes, but, you know. Okay, number 14, sodium, and then with, I can't remember if it's called hydrogen carbonate or bicarbonate on yours. Hydrogen carbonate? Okay, so sodium hydrogen carbonate. Anyone know what the common name for this stuff is? Nope. You use it all the time. It is. That's baking soda, sodium hydrogen carbonate. Okay. And number 15. How many people wrote phosphate for this? Okay, because it's also this is one of the weird ones. It could be an ion or it can be a compound depending on how the electrons get arranged. But if it doesn't have a charge beside it, or it isn't part of a compound like cyanide was here, we name it like a compound. This is phosphorus tetraoxide. Okay, how are we feeling about that stuff? Fairly confident? Okay. I mean, obviously these last few are new, okay, and it's going to maybe they take you a little bit longer, but they still follow generally the same rules as before. It's in the table here. It's in the table of polyatomic ions. It's right. It's up here. Permanganate right here. Yeah. If you see more than 2 elements in a compound, you got to go to the table of polyatomic ions. Because technetium's a metal. Yeah. So it's still an ionic compound. Yeah. Okay. Any other questions there, guys? Okay. Now. Now we got to go the other way. So we've been working on how to do the names. Now we're going to work on this part.